We have some trouble with the Zoom with the bar again.
Oh.
Basically, I cannot connect, so I will have to.
Hola, hola.
Hola. I'm multiplying myself. As you can see.
Like spot the
Okay.
front, left,
No, I cannot make the micro work at the same time the speakers.
What one means? This.
This volume is connected to the USB is here. I can try the other one. And
It's not that Zoom is choosing to use.
Zoom is not working here.
Yeah.
It's getting the input for the micro. But when the micro is working, the only output I can put is the speaker, the laptop speakers. So I can make it work like this, but I don't know if it's going to be loud enough.
Phones and the laptop.
Done it, but it's not working. When I connect this, it's only working through this, but then through this, the micro is not working.
So the problem is when you try to have both simultaneously, right?
Yeah.
Why don't the speaker get the talk? The speakers.
Yeah, we have to do something like that because
front, left, right.
okay, so see if I can make this. No. Okay, so to do, let me first change connection. And then the mic is not working anymore.
Well, the system is getting the microphone, the Zoom isn't.
Yeah, Zoom isn't. The problem is Zoom. And if I change, hi, hey,
Yeah, that is working.
this seems to be working. Okay. Hi, Gourab. Can you hear me? Right.
All right.
This is the laptop. Okay. Okay. Now it should. Hi, Gourab. Can you hear me?
He's muted.
Anyone else here?
Can anyone else hear us?
Yes.
Okay. Okay, then I was talking with Gourab a few minutes ago, but let's see. Hi, Gourab. Are you there?
Hello. Yes, I'm here.
Okay,
Okay, so
you
it
can
works
share
finally.
your screen.
Okay. Should I share my screen?
Not yet.
Okay, let me share it. Okay, now can you see it?
Yeah.
Okay.
Okay, you can go on full screen mode.
Yeah. Right. I think it should work.
Yeah. Okay, so after some technical problems, let's start with the seminar today. It's by Gourab Giri. He's working at the Indian Institute of Technology indoor, and he's doing the PhD there. And we're discussing a paper that he wrote a few weeks ago here in the Journal Club. So thank you very much, Gourab. Whenever you want to start, all yours.
Yes. I'm just playing with the box here. I have to remove it. Right. Oh, so I think you can hear me, and the slides are moving fine.
Yeah, can you raise a bit your micro so you can increase your volume a bit?
Okay, so can you hear me now better?
Yeah, better. Thank you very much.
Okay, okay. I'm just trying to remove this taskbar of the Zoom here because it is blocking my presentation from me. Okay, done. Okay. Yeah, I hope now this is fine and everything is fine to go, right?
Yeah.
Yeah. Okay, cool. Hi, so my name is Gourab Giri. I work here in India, in Indian Institute of Technology, Indore, India. I'm actually a PhD student, final year PhD student, and basically a Prime Minister's Research Fellow. This is very prestigious fellowship given, awarded to excellent researchers here in India. And I am almost about to finish my PhD in 2 months or so, and about to leave for South Africa to join there for a postdoctoral position. So today I thought of talking about the merger paper that I wrote, and the title I already sent, but I slightly changed this title because primarily the title was too long. And also I want to touch upon something something slightly related to this topic that I am today focusing on. So basically the title now is the efficacy of galaxy merger in galaxy SMBH co-evolution. So let us start with something very primary or basic that everybody should understand, is that NGC 474 is basically a nearby elliptical galaxy, and it has been known from quite a long time now, and it has been imaged quite a long several times. And you can see this is the latest image, like in 2022. What you can see is here. The central black region, the blob at the center, you can see is actually the galaxy, the elliptical galaxy. And whatever you see outside, outskirts are basically very faint, some difficult topologically distributed stellar distribution, whose formation mechanism origin is still debated. Okay. Now, obviously, the people who know that they come from merger, and it is quite well established, but still, what is the process of forming such structures is not well known. For example, let us do a simple task. For example, if you have a lake, okay, and in that lake you throw a piece of rock, then obviously you will see some kind of ripples or waves will generate throughout this lake, or at least up to some region. Now, if a satellite galaxy comes and falls into this primary, the central galaxy, and it creates some kind of density wave or ripples that can create this kind of structures, it is also possible. Also, it is possible that nothing like that happened, but a completely different galaxy comes and collided with these galaxies and forms such kind of structures, very peculiar structures. Now, it is very tough to disentangle that what process is happening, okay? Now, for the first process that I told, whether it is possible or not, it is quite tough to answer. But if you see this image, okay, this is one of the galaxies. This is obviously simulated structures, but similar structure can be observed in reality. These are called cartwheel type galaxies. These are basically formed of an outer ring and inner ring, and they are joined by spoke-like structures. Now, the main governing mechanisms that have been produced through simulations have been observed that there will be a victim galaxy, and there will be an intruder galaxy which will just hit it from the center, and it will create some density wave which will propagate, and it will create a ring-like structures. So the first formation mechanism that I told is not impossible or implausible. They happen in the universe. Now, whether this is happening here as well, because you see in the rightmost part of this image, there is another galaxy, spiral galaxy, known as NGC 470. This galaxy is actually telling you that this kind of scenario is possible. However, thanks to the simulations led by Bilek in 2022, this is the result they have produced from their simulations, and they told that it is not the NGC 470 that is colliding and creating this kind of structures. There were another galaxy, spiral galaxy, which actually collided with it long back, and then it completely dissolved into it, and then created such kind of structures. So by looking at the image, you cannot actually contradict, or you cannot predict something that is, prediction will be very biased, and that's why people still don't know the formation mechanism of NGC 474 yet. This is one of the mechanisms, but other mechanisms is also possible. Okay. Now let us go further. Now, given the choice, given the theory that galaxy merger or collision happens in the universe, we have already seen them, and then the question is what kind of structure they associates. I mean, if a recent merger have happened, if it is happening like 3 gigayears ago or 4 gigayears ago, then it is very tough to find a signature, because these faint structures, the outskirts of, that are found in the outskirts of the galaxy, they actually became too faint to be detected after 4 gigayear, or maybe they completely dissolved into the host galaxy. Now, if a recent galaxy collision happened, then what kind of structures that we are targeting for? That we need to know, because the way they leave their stellar distribution in the sky can give you some information about their trajectories, how they collided, and then it is the job for simulation people to take these informations and produce them, whether this is the formation mechanism. This is how they are interconnected. Now, for example, if you see this image here, where 2 spiral galaxies are colliding, you can see it is creating a prominent tail structures in both side of the in the left and right direction. and eventually they will merge and collide, and it is expected they will form an elliptical galaxies, not necessarily, but expected. But you can see this tail kind of structures which is faint but prominent. Now, what other merger related structures that you are expecting when you observe some galaxy, and you can say that okay, these galaxies have undergone some merger? I have listed here some in red. For example, you can see there is a tidal tail structure, there is tidal fan, sail, ring, stream, boxy and disky isopod of the stellar distribution, dust lane. Many things can be possible. People have individually studied them, but not statistically have concentrated them, like to disentangle them in some ways to understand what kind of formation mechanism is there, what kind of means whether there is a minor merger, whether there is a major merger, this kind of structures. Now I am showing you here one image here. You can see this collage of elliptical galaxies. Here the elliptical galaxies is quite clear. It has a very elliptical shape and nicely captured. But in the center, if you observe, then there is a disk that is completely embedded in this galaxy. I mean, this is quite surprising because it is not expected. Okay, so if this is happening, I mean, this is not also a very uncommon structure. You can find, if you lead a statistical sample of elliptical galaxies, you will find some. And people have suggested that recent major merger have occurred which leave the stellar distribution near the center disky, which will eventually dissolve into the elliptical galaxies. But as they are very recent, so they maintain their diskiness in the center. Now, a counter example of this can be this, which I obtained from Dark et al. 2015. This is basically Atlas 3D sample. Here you can see the central blobby features, the elliptical galaxy is there, no problem. But in the outskirts, you see there are lots of faint structures with complex topologies. You can see, for example, in this image here, in this image there is this, as well as here. The most complex of them all is this one, which is telling you that of course there is a merger happened, because this much complex stellar distribution might not be produced in any ordinary event, for example, outflow from galaxy or starburst outflows, anything. This is very specific, and it indicates that something have crossed over this path and eventually collided with this galaxy. Now, these are counterexample to the previous one, because it has been investigated in several studies that these tracks of star that are there captured, they actually tells you the satellite galaxies or very small galaxies that is gravitationally bound to these main dominant elliptical galaxies. They eventually comes and collide, but during this time, whatever path they take, they make their imprint by keeping their stars in the sky, like spreading it, because it is gravitationally it will be distracted. Am I audible? Because it says internet is unstable.
Sorry?
I hope I am audible, right? I hope I am audible. It says my internet is unstable slightly.
Yeah, because of the internet connection, but we don't see that.
Okay,
Go ahead,
okay.
no problem. We can hear you well.
Okay. Thanks. Okay, now let us go to something really fascinating images. This is a very famous galaxy. This is called Fornax A galaxy, and if you see, this is been imaged by Hubble Space Telescope, and you can see that the central zone, the central region is actually the elliptical galaxy, where you can see the clumpy star distributions there. But in the outskirts, in a large galactocentric radius, you will see a distribution of stellar star, but they are not homogeneous or isotropic or anything. I mean, you can see there is a structure that looks like cell. There is a structures that look like filaments. There is a structures that look like stellar streams. So what is happening in this kind of scenarios is obviously a merger, but how this is happening, nobody knows. For example, if you see in the background of these galaxies, there is another galaxies which is also showing some disturbed signature, but it is not certain that this interaction between these two galaxies have actually formed this outer very faint stellar distribution. There are lots of studies who actually simulated this galaxy and told that it is some other galaxy which were there. They interacted with it and created such structures, and currently the background galaxy is interacting. Now, if you zoom into the center of this galaxy, then a very interesting features pop up is that there is a huge amount of dust lane is found, and if you look at the orientation, they are not randomly oriented. They are kind of in a what so say in a disky fashion. They are distributed in a disky fashion. So these kind of signatures are basically signatures of merger, because it is not expected in elliptical galaxies, but still we found them. And sometimes these galaxies are found deformed companions. Okay. Now, this is all fine. All of these images that I saw is in optical, either R band or any other bands. But what about other wavelength? For example, if I show the same galaxy, Fornex A, in radio band 1.4 gigahertz, that is captured from VLA, then what will you see is the blue image here. Now, the central part is very bright because there is a central supermassive black hole and kind of which is kind of emitting a jet. It's kind of boosted, and then it is I mean, the central black hole that is ejecting the jet, that is getting terminated somehow in the outskirt region and creating this blobby feature. So this is actually a jetted galaxy. Now, the energy stored in this blob is 10 to the power 60 arc. This is huge. And that's why they are called one of the powerful events of the universe, the jet, propagation of jets and termination. Now, it is obvious that this much of energy, when it will be transferred to the surrounding medium, then obviously it will be affected. The ambient medium, the galaxy itself, it will be affected. And if I give you the composite image, for example, this the rightmost image, you can see there is a the optical image in negative form, and there is a radio contour. You can see the size of these structures, combined structures. To guide your eye, I can give you this image. This is quite a good looking image. So basically what it tells you is that when two galaxies collide, they affect each other so much that their evolutionary trend can be affected, because obviously you will not see this radio-jetted structure in every merging galaxies, but merging galaxies show this kind of structures. So this is quite strange. So this actually proves you that we need to seriously take galaxy evolutions like they affect they govern the evolution of galaxies, also the nearby ambient medium. For example, this galaxy is embedded in a cluster medium, and it will definitely affect the cluster medium as well. Now, with these motivations, I actually lead my recently published paper. I thought what will be the easiest way to understand a merger? What kind of merger have happened? So I want to see, I just want to have some images, and from that images, can I infer something about the underlying mergers? Whether this is possible or not, that is one of the main motivations of mine. The other is like, so there are 4 things I have listed. Is there any relationship between the structures observed topology, the morphology basically that you observe, and the details of the underlying merger, which I already told that there is some features, the stellar streams that actually tells you the orbit of the colliding galaxies. The second motivation is merger the primary source of evolution in early type galaxies? What is this early type? What is the in the local universe? I mean, people have studied, lots of studies are there who studied the merger fraction in local universe, also in the high redshift universe, but they have actually concentrated, like they took the sample of galaxies and they found the double nucleus, and they just did the analysis of how the galaxy rate evolves. but there could be biases because elliptical galaxies is more prone to collisions because they remains in the end of the mass assembly process, whereas spiral galaxies are still evolving. Also, the process of identifying the merger, like identifying two bright blobs or center, is not a good proxy. So this is also what we want to take consider of, that in the nearby universe, whether what is the merger rate or fraction of early type galaxies. The last one is, can the merger structures be classified into different categories indicative of possible origin histories? So these are very simple questions. I just want to explore that from simple images. Can we say something? Okay. Now, this is the first part of the talk and major part of the talk that I will be focusing on, but I will also talk about my recent work that is connected to mergers and how it is affecting the galaxy also. Now, let's focus on this first part and start with our sample. What we did is, there is a SDSS lead this IAC Stripe 82 legacy project. What they have done is, they have scanned the Stripe 82 region, RADIC is given in the lower here. So they have scanned this stripe for multiple times. And what they have done is they have co-added them. And this gives those bands a very deep magnitude in R band, like 28.5. And they are, this is okay. I mean, I will say this is okay to conduct this kind of studies, because the stellar distributions that remain in the outskirts or even in the inside of the galaxy, they are typically very faint. The intensity of those structures is less than 5% to the total galaxy in most cases. So you need deep images, and 28.5 is just fine. However, there are even deeper studies like 29, 29.5, or even with dragonfly telescopes. But I believe this is fine for now. Now, what we did is we selected the nearby galaxies by implying a redshift cutoff like 0.05 up to 0.05, and also we want to apply some techniques there, because these structures will be hidden inside of the galaxy in the smooth distribution of stellar distribution of the galaxy. They will hide, and also the outer structures, they can also hide in the sky background, because these are deep images. So what we did is we put a cut in Petrosian radius that it has to be greater than some value. So basically, a good amount of size, the size to make our operation prominent has to be there. Now, once we did this, and once we start analyzing the samples, we see some good structures in the outskirts of the galaxy. For example, here I have shown some examples in the image A. You can see the central elliptical galaxy, which is kind of a spheroidal shape. But in the outskirts, there is a faint cell-like structures. Okay, there are lots of tiny blobs here. Those are basically foreground stars or background luminous objects. But more or less, you can see that there is a stellar distribution that looks like a cell. Here also you can see there is a galaxy, and there is a clump of matter in this B image. There is a clump of matter just outside of the galaxy, and also the galaxy is not totally elliptical, but there is a disk kind of structure inside these galaxies. So this is indicating that something has happened to that galaxy. And there are other examples. For example, if you see the third image, there you will see lots of stellar streams. Lots of means 1, 2, 3 is dominant. There is tidal tail in the D. There is a very faint dust lane. You can see the dip in emission. I hope you can see. It's very deep in emission. So these are indicating that there is a very prominent dust lane coming from the center towards the outskirts. And in the bottom two image, I have shown some galaxies which are totally disturbed, like very highly disturbed galaxies. So this is some of the classic example that I saw, that I mean, when you see those images from original images, I mean, they are so intense, these structures are so prominent that you can find it out in the original images itself. But I must mention that this is not the general case. Okay, you need to apply techniques in order to find them out, because as I said, the intensity mostly becomes less than 5% of the host galaxy. So what we have done is we have used two different techniques. We had to do this because, let me tell you first, the usurp masking. It's very standard way of identifying merger structures, but there is problem with answer masking. Okay, answer masking is basically you take the galaxy image, okay, and then you blur with a pixel size, and then you subtract it. Okay, in this way what happens is the average stellar distribution of the galaxy will be removed off, and whatever asymmetric structures there are lying hidden, you can find it out. You can clearly see it here. For example, if you compare image A, which is the original image, and image B, you can see for a particular choice of sigma, you can see that the outer structures are coming out to be outer and inner structures. You can see there are cells there which are coming out in the answer masked image, because the average Gaussian average galaxy intensity has been removed. But the problem comes when you vary the sigma. Okay, for example, this lower left image, this image where f denoted as f, here the value of sigma is basically 11. So the sigma is actually smooth you want to make the profile. It's a user's choice, and you can choose any value. So we started with any value, and when we put 11, you see that the central structure, the cells that are lying very near to the center, is actually getting totally destroyed by the techniques themselves. However, the outer structures coming out to be very prominent. The outer cells are coming out to be very prominent. However, in this figure B, when you have a lower sigma is basically 3, what you got is outer structures intensity is not as much as in F, but you can start finding out the structures that are lying inside. So this made us screwed, because now you don't know which sigma to choose, and in your statistical sample, like we have 202 elliptical galaxies, and in your statistical sample you have to now apply this answer masking. If you want to use them, apply all like use answer masking, but with every sigma. Like we have gone up to 11, from 3 to 11. So from sigma 3 to 11 we have applied them all, just in case we don't misclassify any structure. That may be an artifact of the techniques itself. Still, we are not very much convinced about this answer masking. It's a good technique, no doubt about it, but we need to confirm it from other independent techniques as well. So what we did is we went to model subtraction. So basically what it does is it creates isoforts around the center. You give some parameters. Here are also, there are lots of free parameters. For example, the center of the galaxy, the ellipticity of the galaxy, and the position angle of the galaxy. Now, okay, there are lots of combinations there. Now, while we are applying these techniques, we also found some problems. Now, based on how you model them, right? Like free all the parameter, you just give the initial point where you think is the best. You just give it initially, and then you free the parameter. It will automatically find the algorithm that how to fit isoforts, and then it will create a Gaussian. It will create an average galaxy intensity image, and then you can just subtract it. But while we are doing the other stuff means we want, for example, I personally wanted to fix the center of the galaxy, because if you just vary the intensity, these are deep images. So if you just vary the intensity, you can find the center position. So I wanted to fix the center. At least this will give us more freedom in terms of parameters. But then whatever we got is not at all whatever we are expected, because this was over subtracting in one side and under subtracting in other side. So in this way, we tested it also thoroughly, and what we came up with is you just give the initial values by just giving an initial fit. Just do one fit, and then you find out the best possible parameter that you like, and then give them and tell the software that don't fix anything, you do as your algorithm tells you. So you can see we have tested this technique in Tal et al. Sample. It's a very famous paper. They have actually done some good deep imaging at Yale. And you can see this is IC1459 galaxy. And when we applied that technique, we start finding out these cell structures, both inside as well as outside. The inside structures might not be that clear in your screen, but we have found them. So after doing all these testings, we are kind of relied and we started to identify the merger structures, and we will tell that there is a merger structures if we found something both in answer masking and in model subtraction technique, as well as while we vary the intensity of the original image, we should know that there is something to avoid the artifacts. Now let's go to something. Let me just divert to somewhere else slightly. Now before I jump into I have applied those techniques, my samples are ready. Now what I have to do is I have to take those images, I have to observe them, I have to know that why this structure is coming, what is this structure, and how much of you are getting it in your sample. Now in order to do that, you obviously need to have information from simulation. Now in this work, I have not done any particular simulation, but there are in literature, there are lots of simulation exist which actually targeted one-to-one, like the galaxy that have been observed, and they have tried to produce them through their numerical simulations. I mean, this is the power of numerical simulations nowadays, that you can actually compare one-to-one morphology. Now, the leftmost image I took from Mancilius, which is quite famous paper, and they have actually compared some galaxies here with their simulations. The galaxies are in left side, and the simulated images are in right side. So you can see they have more or less produced those structures observed. However, I must mention that the magnitude of the surface brightness of these images are different, and that's why you are seeing in lot other structures than what you are seeing in the observation. Now I have targeted this particular simulations results. I have find them out from the literature, and I have understood that what kind of structure is appearing because of which merger. For example, you can see that in the middle panel, in the observations, you see a tidal stream because it's very complex and curved. It's a tidal stream. And this kind of structure is also produced here. And they have actually given the parameter space that if the mass ratio of the colliding galaxies are this, then you are finding this kind of structures. And if you see the morphology. So this is particular some examples I adopted and I utilized further in my samples. Another example is this Wang et al. 2020 paper. This is a very famous galaxy. This is Centaurus A. It's a very famous galaxy. It has been observed in multiple bands many times. You see in optical band, you see this kind of morphology, and in the right, in the gray scale, all of them are different models, and the model 10 best matches this. So in this way, they have actually explored all the parameters, and they tell you that if you find this kind of structures, then the mass ratio, what could be the mass ratio? What could be the evolutionary phase of these galaxies, right? So I have adopted this, and then I have applied those informations into my images. But before I go to that, I just want to highlight one more simulations. This is quite old paper from Hörnquist and Quinn, 1989, most probably not 88, 9. So here you see that the cross mark is actually the potential of the heavy galaxy, and there is a satellite galaxies which is coming and falling into this potential. And you see for a particular orbit, you see the evolution and how they are forming an X-shaped X-like morphology. It's a stellar distribution of X, giving you an X-like morphology. Now, this is one of the complicated structure that we also obtained, and it says that the minor galaxy, the mass ratio here is almost 1:100. So basically, this minor galaxy, when it falls, it has to be falling into a specific direction. So this means that you can actually find out some signs from by looking at the morphology of these galaxies, of these structures. Okay. Now let us go to our sample again. Let us look at image A and B. Okay, these are representing the tail structure. Okay. Now in figure A, the tail is very straight. The stellar distribution is very straight and thin, well collimated. However, in B, the tail that you got is quite curvy and broad, diffused. Now, similarly, I went back to the simulations. There is a very recent simulation by Ren, and what I found out is that whenever you see very thin, well collimated tail-like tree, that there is a very minor galaxy that have been collided with these galaxies, and this hypothesis has been supported by a cell. You can see a cell here. I hope you can follow my cursor. You can see a cell structure here, and cells are majorly come from minor merger. Okay. Now in this image, these broad diffuse curvy tails are coming out because of major merger, and there are lots of simulations which confirms it. Let us go to the next images, for example, C and D. These are called tidal fans. Tidal fans are generated when two elliptical galaxies collide because they have random velocity of stars. That's why when they collide, they kind of create a tail at the first few billion years, but then they start to diffuse away. So in C, you can see there is a very mild signature of tidal fan. I hope you can see it. There is associated to the tiny galaxies here. But here, the galaxies which are colliding, you can see there is a tail information. There is a fan information, and it is quite broad. In the C case, the tail is quite very narrow and not very broad spreaded. Now I can give you another various examples that are quite well available. For example, let me just give you, maybe I can give you later. Lots of examples are available. You can just Google it, tidal fans. But our exercise is slowly and steadily telling us that yes, you can infer from the morphology that what kind of merger have happened in order to generate such kind of structures. So we told ourselves that this is a good finding, because before you go into lot deeper analysis, for example, the spectra, the star formation rate, the other things, you first look at the image and you first think that what kind of merger could be responsible for such structures. This could be an initial step to know that what is happening to the system. For example, if I just give you another example in the down here, where here E and F, if you just focus on E and F, okay, this is quite interesting. Okay, when I first found it out, I got totally confused. Okay, because of the structures that is here. Okay, and then I dig down the literature, and surprisingly, people have discovered such kind of structures. Some Japanese group, they actually found such kind of structures in their Subaru images. What is happening here is there is a central galaxy and there are lots of cells around. Okay, there are lots of cells around. Now, I already told cells are mostly coming from minor merger. However, recent studies have started. Recent means Pop et al. 2017, 18, 19. These studies currently telling you that cells can also originate from major merger. Now, what is happening? There are lots of evidence of cells. However, in the down region, in the bottom region, there is a stream. There is a stream of matter which is ending in a clump. This is quite strange, and at first thinking, I thought this could be a tidal tail. But this is not a tidal tail, because if you see the simulations of Mancilius, I hope it has it here. No, it is not here. Sorry. So if you observe the simulation of Mancilius, they actually showed you that this is not a tidal tail structure. This is a stream, And if you have more deeper images, then you will be able to track a closed loop here. So these are actually indicating that these are minor merger structures. However, here, if you focus on F, then it's a clear sign of a tail. Okay. And the cells that have been found here is quite prominent and aligning along the major axis, although there are perpendicular cells as well, but they are mostly aligning along the major axis. So this kind of cells from simulations, they predicted that they are coming from major mergers. Now I can give you all these examples G and H where dust lanes were detected. Like in the H image, in the original image, we see no evidence of dust lane, but when we do the operations, we find out that near the center there is a dust lane, and in the G there is a broader dust lane which you can see in the original image itself. Okay, there are stellar streams and structures. So basically, we slowly and steadily convinced ourselves that yes, based on morphology, there could be a possible distinction between different formation process. Here I am just keeping some complex structures that we discovered in our image, not discovered, we found out in our image. So here you can see when we applied our techniques, these prominent X-like structures appeared. I already showed you how the X structures can appear. In the bottom panel, there is a ring structure, and you can see, you probably can see the minor galaxy which have recently collided with these galaxies right in the bottom right corner of the center of these galaxies. So basically these are deformed rings and these are signatures of merger, but these two are basically minor merger signatures. And here some of the very peculiar structures that are coming from major mergers. For example, you see the last image, bottom right. You see the elliptical galaxy actually took a shape of a box. Now these are called boxy structures. They are not common and they appear from multiple dry mergers. Dry mergers mean, of course, elliptical galaxies comes and collides. Lots of elliptical galaxies have undergone merger here. So they can generate such kind of boxy structure. And there is disky structure. As I told you earlier, I showed evidence of it, that recent major merger with a disk galaxy have happened. But as it is a recent merger, I mean, the structure is not yet dissolved totally. Okay, it's still there. The disk is still maintained there. You cannot maybe see it in the contour plot, but when you do the operations like answer masking or model subtractions, you will be able to find a clear disk in the center here. Okay, these other structures are also very rare. No, the upper structure is very rare. These are called the spiral structures. So a very spiral disk keeps its spiralness intact and it kinds of hide inside elliptical galaxies. You have to apply the techniques in order to find them out. And in the bottom, if you follow the white lines are actually the isoforts. If you follow the isoforts, then you will see that the isoforts, initially the major axis was along these directions, but slowly and steadily they rotated and flipped in these directions. So these are called isofortal twisting because of recent merger. Obviously the sign of recent merger you can see here. If I give you the full image, then you will be able to see there is a cell and tail present there. Now going to further to our motivations, that can we propose initially, just to tell ki if you are finding this kind of structures, then what to expect. And yes, after all the analysis and after gathering all the knowledges of simulations and observations from literature, what we found out that if you divide the structures, early type galaxies, merger signatures in early type galaxies based on these 4 classes: relaxed, recent minor merger, recent major merger, and ongoing interactions. These are not very new. I mean, this classification is not new. I have not proposed it. These have been already proposed by Dark et al. In 2015. The group of Atlas people, they have already divided such structure. But this time what I did is, I defined that what to call a minor merger, what to call a major merger, and then further sub-classified those major classifications into, for example, recent minor merger into 3 categories: mergers having big mass ratios, for example, from 0.1 to 0.7, mergers having intermediate mass ratios. These are the mass ratios of the colliding galaxies, okay? From 0.01 to 0.1, and small mass ratios. These are basically very tiny galaxies that are falling, satellite galaxies, less than 0.01. They can only produce stellar streams and palms. These intermediate mass collisions can create shells, stellar streams and palms, and X structure. These mergers, which are kind of very prominent, they are minor merger but prominent. They can leave some signature in the host galaxy for a long time. Though those includes tidal fan, thin faint tail, collisional ring, cell, outer dust disk, disturbed structures. These are the structures that we fall in this category. However, while we are doing the classification of major merger, we are screwed again because in major merger we give a very narrow range of R from 0.7 to 1. This is a very narrow range to classify structures according to these categories. But we figured out that there is high mass ellipticals and there is low mass ellipticals. Low mass ellipticals are typically less than 10 to the power 11.5 solar mass, and high mass ellipticals are greater than 10 to the power 11.5 solar mass. These are quite standard, and people have actually defined them in this way. But when I started to understand the simulation result, the morphology that are appearing from collision of such structures, I am again clearly be able to distinguish between these structures. For example, in low mass ellipticals, you can expect disky isophore, you can expect long curvy tidal tail, you can expect cell, highly disturbed structure, isophotal twisting, stellar streams and palms as well. This is quite strange, but yes, we found some evidences of stellar streams and palm associating a major merger. In high mass ellipticals, these are basically red and very high mass elliptical galaxies, and mostly boxy isophore, tidal fan, disturbed galaxy, and isophotal twisting, very mildly rotating isophotal twisting is expected. So this is one of the striking results that we proposed, and I believe that before we go into deeper analysis of anything deeper spectra or something, we should at least get the images. If deeper images is available, that's fine, and try to see the morphology if these galaxies have undergone into some merger and what kind of morphology is appearing and what to expect. This is one of the important results, but the last conclusion is even more interesting. For example, here I have noted down a table that in our sample of 202 early type galaxies, we found relaxed galaxies 31, which is 15%. This may looks very high, but various studies have actually found them. Minor merger is 57%, major merger is 27%. These are all in the local universe. The most interesting part is the mixed merger. There is clear indication of mixed merger in some samples, which are consist of very less sample, but I think they need our focus now. They need our focus because major merger can change the morphology or evolutionary path of a galaxy, but frequent minor merger can actually, without major merger, if frequent minor merger is happening to a galaxy, that also can change the morphology and evolutionary path of a galaxy. So we found mixed merger case like 2, but multiple minor merger cases like 5. They are included here in this sample, 115. Multiple minor mergers. So the list the catalog that we published with our paper, they consist all these informations, and I think we need to focus on these particular cases because they are less explored, and we believe that they play a crucial role because minor mergers are mostly expected. But the highlight comes highlight comes when we supplemented our result. For example, if you took the Mancilius result, they have done the simulations and they particularly showed that if you have a galaxy with lots of structure, and if you see it in 33 magnitude per arc second square, and then you see it in 29 magnitude per arc second square, this much difference will lead you 2 times lesser detection of structures. So this kind of conclusions, when we supplemented with our result, we came to a conclusions that most, if not all, early type galaxies in the local universe are continuously evolving through galaxy merger activities. This is quite a strong statement, but I think we will be able to prove it with deeper images. for example, like 29.5, like Atlas, or even deeper, like with Dragonfly telescopes, although they are not made for large scale surveys, but still we can do it. We can prove this prediction with deeper images. Now, what is next? What is next is, of course, to get deeper images to make more statistical sample and analyze them. But also, now the TNG data are available, and the most updated TNG data will be available very soon, I think maybe in a month or two. So we can take those samples out and we can do a similar work there in terms of simulations. Right, like I want to extend my talk slightly beyond this, and basically they all are connected to mergers. What happens is, I told you that these mergers sometimes trigger the central active galactic nuclei. Those are basically the supermassive black hole. They sometimes trigger them because they channels lots of matter into the black hole, and those black holes emit jets with large distance jets. Now, I was actually I was doing my PhD in these structures as well. I was also studying the jetted structures, and we discovered something in VLA. This is a galaxy 2 MASS J1203, very complex name. Okay, so this is a galaxy. This is completely in VLA, in radio 11.5 gigahertz. Okay, so you cannot see the stellar distribution here. Whatever you see is the core here. The core, the center of the galaxy, and total structure is 2 kiloparsec. So whatever is happening inside the galaxy, okay. So there is a core where the central supermassive black hole is there, and it is ejecting a straight jet like this. Okay. These are the hot spots where the jets terminates. So there are ambient gas, the gas of the galaxy where the jet collide, and it creates hot spots. That's quite fine. Okay, cool. But you can see lots of this jet material. These are actually plasma material. Lots of this jet from these hotspots. Not only in this side, but also in this side. The bend, and the people who actually observed, they are our collaborators. They find it out that the central black hole, the jet is kind of curved. The jet is not straight going. The theory says that the jet has to propagate along a straight path, but it is not going along a straight because the jet is kind of precessing, okay, around an axis. Now, if a jet is precessing, that means the black hole has to precess. Otherwise, how can you precess a jet? Now, what can trigger a black hole to precess? Because black holes, these are not stellar mass black holes. These are supermassive black holes lying in the center of the galaxy. Now, this is actually the motivation to extend our work here. Because the prediction is the galaxy collision that is happening, that I already showed you, like this, all these galaxy collision, they can provide their own black hole to the progenitor galaxy. Now, in galaxy collisions, it is possible, although only handful, like 7 or 8 have been discovered yet, binary black holes discovered yet, because of existing resolutions. I mean, current day telescopes are trying to achieve that resolution, but it is possible. Okay. Now, in order to do that, this is the observed image. What we did is we wanted to simulate this. Okay. So these are all relativistic magnetohydrodynamical simulations. So we treat them as a fluid. So we made an initial setup, and this is basically the bulge of the galaxy. So whatever happening inside this gaseous bulge of the galaxy, because they have predicted that the galaxy to be a spheric, S0 type, and that structure extend up to 2 kpc. So whatever is happening inside that bulge, you generate a bulge, and from the center of this structure, you inject a jet, but that is precessing. You inject not a straight jet, but precessing jet, and you just leave it there, leave it to evolve, and you find it out what is happening at a later time. This is a dynamical structure in the right. You can see that the jet is kind of precessing. The jet is showing in helical structures. Okay, that's very cool. But how do you explain the emission? So this structure, when you see from a particular line of sight, I will not go into the details because this is something I don't want to conclude somewhere. When you see these structures from a different line of sight angle, and you do, because whatever you see in sky is basically a 2D projection of the 3D structure, right? So you have to make these intensity surface brightness maps. So when you do that, you kind of find it out the morphology is appearing to be appearing to be very same. So this morphology is same, meaning that the jet is precessing. So our study confirms the jet is precessing. Now, if our study is confirming the jet is precessing, then it has to be, there has to be the black hole. The black hole is kind of perturbing. So this means these galaxies have undergone a recent merger. Okay. Now, of course, there is some problem. I mean, in observations, they have underestimated some parameters. We have corrected it and see how close we get. And then we predicted a polarization map of it. Now, anybody can go into VLA and propose that I want to see it in polarization band, and they can verify our theory. But the moral of the story is, there is 3 points I want to give. Galaxy merger is a crucial process of galaxy evolution, at least in the local universe. This comes in terms of both their own stellar evolution as well as their gaseous evolution, as well as they affect the ambient, the surrounding medium. For example, I have shown you images where the cluster medium is getting affected, and the emitted and very violent energy emission process. The spatial topology of merger remnants can be used as an initial step to understand the underlying merger. Carb-jetted sources like the one that I shown are becoming the potential candidate of hosting binary AGN, means binary supermassive black hole in their center, possibly originating from a recent galaxy merger event. So these are the 2 papers. This one is the recent paper that I published, and I have been invited to give a talk. I'm really grateful for that. Thank you. I conclude my talk here. Thanks.
Okay,
Hello.
thank you very much.
Hello.
Questions?
Okay.
Andres,
Should I-
you may approach the.
Hi, Gourab. Thank you for very nice talk. I have a question related to the 3D orientation of these systems. What will be the consequences of observing one of these, streams or tidal features from one or another orientation? Because my guess is that you could confuse one by the other depending on whether it's aligned with the line of sight or not, or these kind of things. So I don't know if you have any comment on that, or.
Okay, just let me clarify this. So your comment is on the last one where the jet is ejecting, and how can you say that it is reorienting or precessing, right?
Sorry, say that again.
So your question is on my last project where I have done some simulations on ejected jet, and
No.
question is how I am saying that. Oh, okay.
No,
Okay,
but
then
in
I have
the merger,
Yeah.
in the traces of mergers in other galaxies. So when you
Yeah.
observe like streams, when you are categorizing them, like whether have you
Yes.
checked, or whether do you know if the orientation of the system could impact your classification?
Yes. Okay. Yeah, that's a very good question, and I want to mention that in our paper we have actually done them. So basically, we have again adopted the prediction of numerical simulations. For example, the Mancelius, Wang, they have all done the simulations, and they have varied the projection in order to see that whether the structures are coming out to be what we are expecting or not. What it appeared to be is, for example, if you detect a cell, if you make the orientation change, the cell structure will remain as cells. It will not appear as any other structures. Now the question is whether they will fool you what kind of formation mechanism is happening. Now for that reason also, they have done multiple simulations, and they told that there is a particular alignment process. For example, if the alignment is happening along the major axis of the galaxy, then it is most likely to happen from major merger. And if it is appearing randomly, then it will be minor merger. However, the cells will remain cell. It will not behave differently. For example, in tidal tail, the confusion may happen in tidal tail or streams. People can happen. In that case, as our sample are quite nearby, okay, so what people predicted is that you can rely on intensity of the intensity, means the prominence of the structures. So there are lots of people, even the Dark et al. Who are Atlas group, they told that you can rely that if the structures is complex, the topology, the morphology of the structure is complex and thinner, then obviously that will gonna give you it's a high chance that it's gonna be a tidal stream. And if you see a not so complex but curvy, broad, diffuse diffuse structures, then it will be a tail. So till now we have based our thinking procedures on them, but as I said, there is a future scope of doing such statistical study from TNG data or any simulation data that is available. Yeah.
Okay. Thanks. More questions? If it's similar, it's better. Okay.
Okay, so about so thanks a lot, Gourab. My question is about the subtraction of the profile, especially the one where you showed the X-like shape in the center of the galaxy after you subtracted the profile. So I've seen these cases, but when I usually see these, it hints to me that I've estimated the wrong ellipticity and the wrong axis ratio or position angle for the galaxy. And it usually happens in those cases that you were also showing where the isophotes have different elliptical properties. So have you tried subtracting the profile from one of the galaxies with different isophotal elliptical properties to confirm that this X is not due to having different isophotes? Isophote ellipticities.
Yeah. Yeah, that's a very good question, because when we start the project, we encounter this kind of problems. So yes, we have tested them, and when I am showing you some X structures is appearing there, so that means we have actually done lots of testings there, and the X structure is quite prominent in original image also. So if you vary the intensity, it's very prominent. The some signatures you can see an X structures, but it can be confused with stellar shells. But we have obtained the similar signatures from Gaussian subtractions like answer masking, model subtractions, and other. So that's why we confirming it's a X-like structures. But this kind of things can happen, and we have to be careful about that. So better not to focus on faint X structures. Yeah.
Thanks. I have a question. How do you? It's regarding your second work, the one with the related to the precessing radio jets. Another cause of curved radio jets can be impact of the radio jet with the circumgalactic medium. How do you distinguish when a jet is curved by the collision with the medium from a precessing radio jet?
Yeah, right. That's something I actually working on throughout my PhD. So it's very confusing that when the jet interacts with the circumgalactic medium or even the cluster medium, they can bend the structures because of the asymmetry in the ambient medium itself. Okay, but here the jet is actually precessing. Precision is a very periodic rotation. It cannot be explained based on just diversion. Diversion happen, for example, in X-shaped radio galaxies. There are lots of confusion because there is no precision involved. There is flip, either it's a flip or it's a diversion because of the medium. But here it's a precessing source. It's an S-shaped source. So most likely it's gonna be some complex activity happening in the black hole. And most importantly, when we adopted the parameters that have been predicted from the observations, we have some problems, but then after modifying the parameters, we have got the structures and the properties they have mentioned, everything. So that's why we are saying that it's a precessing source. But yes, it's a good question. Yeah.
Okay, thanks. More questions? Sepide?
Hello, thanks for your nice talk. I had a basic question about your technique for finding the merger remnants. You subtract the main galaxy, for example, 1459. Why the shells is a part of this galaxy? Why are you subtracting the main galaxy? Why you don't subtract the extra object in the image and looking for the merger remnants?
Okay, so are you referring to the extra images like the blobs that are there, the foreground or background luminous objects?
Yes, in your, could you go to your first slide? In
Yes.
technique, you found a shells, your,
Yeah, this one.
go back. Another one, yeah, this one, the 1459. Why you
Yeah.
subtract the 1459 and while the shell is a part of this galaxy, why you didn't subtract the background or foreground objects?
Oh, okay. Oh, yeah, we have actually subtracted them. So in order to show them, this appears. So what we have done is, while fitting the isophores, we have actually masked all of these luminous objects. We have masked it completely. So while doing the fitting procedure, while doing the isophores, it will not take the values of these galaxies, and that's why it is fitting it. But when you do residual images, what you do is you have an original image, and from that image you subtract it. Okay, so these structures, the faint structures, are starting to appear. So we have actually taken into account all the structures.
Thanks.
Thanks. More questions? Okay, if we don't have more questions, thanks again, Gourab, for the talk.
Thanks. I mean, I'm really grateful that you invited me for this talk. I'm really excited to look forward to interact maybe.
Okay.
Okay.
Thank you very much, Gourab.
Thanks. Thank you.
Bye.
Bye-bye.
You're welcome.
Okay, so should I leave then?
Yeah.
Okay.
I
Okay.
recorded